Welcome back to Book Club. And we're in applied numerical methods. It doesn't have to be Python, it can be MATLAB, it can be whatever you want, but this is kind of your basic book of computing and solving engineering and physics and chemistry problems with computers. And kind of gone through a lot of basics, some more advanced stuff, and really most of these have to deal with consequences of digitization and discretization. And last time we went through integration and differentiation, and this time, if you will, that's where you have, you've got a set of points that you have a function that's known, and you're trying to either get the derivative of the function or you're trying to understand the area, the integral area under the curve. So ordinary differential equations, or ODE, which is where we are today, this is, say this might be time, this is t0, the starting point, and usually you have some information on the slope, and that you have some sort of differential equation. And so a lot of times, we'll write this as dy dt as some function of both t and y. Usually because that way we're sort of used to this being the y-axis and this being t. And so what's known at every point is the slope, and you have to basically integrate your way forward to figure out. You actually don't know this. This is now function of t, the variable, is unknown. Okay, and so the couple of methods that we use to do this. A lot of it's still basically back to the Taylor series. Okay, in fact, the Euler method is just a very basic version of this, where you take this, and this literally becomes y at sort of the next time step minus y at the current time step divided by dt. That's just basically busting that up is then equal to the function, and you evaluate this at the current time step. Okay, this is Euler method, and so you can solve for y at t plus delta t, and you just crank forward. Now there's a convergence. There's a size of this delta t for which this is stable. There's a size for where it's unstable, and unstable could mean everything from you start having oscillatory behavior. It's not just that the error is bad; it's that it sort of starts going nuts. Okay, and you can see this a lot of times on a computer. All of a sudden, it'll be like NaN, like not a number, and so there's sort of error, and then there's stability, which is things just going nuts. Okay. Now a lot of this stuff will then change. It's basically where and how you evaluate this, as well as the form of this. That's the two things you can start changing. Okay, and so there's something called Heun's method, which we'll write down, which is sort of this mixed thing. So what you would do is you would say y 0, and 0 is sort of a intermediate step. Okay, which is you would take the current y, you would sort of integrate it, dt, give them the f of y at t at yi. All right, and then that gives you a y0. And then what you do is that y at I plus 1 is then equal to, again, this original y, so it comes down, but now it's a change, and inserted in here, this is both f at t comma y0, right? So the y0 comes in here, plus f of t at y, the initial time step, and that's divided by 2. Okay, so you're using a different color here. You use the function to estimate y0, and you take that y0 and you sort of reevaluate the function, and you sort of average the two. Now this is second order accurate, so this will drive error like dt squared. Okay, and so what I'm going to try and draw here, I'm going to save this corner for something here in the end, so I might try and draw it sort of right in front of me here. There's a whole set of systems, and I'll write it down here. It's called predictor corrector. Predictor corrector. That sort of involve this sort of trick. Okay, and I'm going to try and draw graphically the Runge-Kutta method. Okay, so look right here in front of my chest, Runge-Kutta. Now this is a set. It's actually a whole set of equations, and what I'm going to try to do here let's see, is the fourth order Runge-Kutta, so RK4. So what I'm going to try and graphically draw. Okay, so the way this works, here's some time t initial, and you use, here's the function f at that time, and you evaluate its slope, and you get what we'll call here kind of step 1. Okay? And then at step 1, you can come back and you can say, I can evaluate the slope at step 1. Now I'm going to come back and use that new slope to come again. And by the way, this is being evaluated. If here's t at I plus 1, this is actually sort of, t at I plus delta t over 2. It's at the half step. I come back, and this is step 2. And then let's say this gives me a new derivative like that, now downward facing, just so I can draw it, okay? And then you come back and you would use that new derivative. Hopefully I got that somewhat halfway okay, all the way to the full time step. And that's step 3, for which I would then evaluate yet another derivative, okay? And then each one of these derivatives, okay, is actually labeled. So this derivative is K1, K2, K3, and then K4. All right, and so then the Runge-Kutta method, and again, you can look this up online, Wikipedia, that's got them in the books, is then the formula that says y at I plus 1 is equal to y at I plus dt over 6, and then you have the set of K1 plus 2K2 plus 2K3 plus K4. All right, so this is I'd say more advanced predictor corrector, but this is accurate dt raised to the 4th. So the 4th order accurate, that's the RK4. Right, so it's this whole set of sort of using, the slope, which is, right, dy dt, it's a function of y, the current position y and time. And so you sort of, you do sort of 2 evaluations at the half step. You evaluate K1 is the slope at initial time, K2 is in the slope at the half step, and then you come back and use that to get the 3rd slope, and then use that to step the full way, get the 4th one, and then sum it all up. Okay, 4th order accurate. Now there's a whole slew of these Runge-Kutta. In fact, even in the book it talks about one of the ways you can do error estimation, right? You can actually use, well, how can I estimate how small dt needs to be? Well, there's actually, so there's a MATLAB, I think there's a Python run called RK45, where you basically just give it the function. You just say, here's the function, please integrate in time. I'm starting at time 0, I need to go to 100 seconds, just give me the answer. And you don't care what the time step is. RK45 is actually then going to use Runge-Kutta 4, and there's a way to basically calculate one more term that makes this 5th order accurate. And so that gets you a way of estimating, is my dt going to be small enough based on the total error I'm looking to capture. Okay, so these are sort of the automated methods. If you ever do like computation of fluid dynamics or different things like that, a lot of times it can be, RK is fairly common there, but there's nonlinear terms. You can actually split how you handle the linear terms, the nonlinear terms, and that can be some pretty, anyways, there's all these interesting algorithms. Kind of back to that curve I used to show a couple times ago on like kind of speed up due to not just computer hardware, but algorithms. This is a lot of part of it. There's so much richness here. So I encourage you to dig in if you're interested. Last piece, then I'll talk about chaos. Okay, so the last piece is stiffness. And if an equation is stiff, it's really because you have, take a look at this equation, which is the time rate of change of y with respect to time is equal to, so minus 1,000 y, you'll see the y in a second, plus 3,000 minus 2,000 e to the negative t. All right, so the full solution, because we could actually do this analytically, the full solution looks like this. Y is equal to 3 minus 0.998, write it down, e to the negative 1,000t minus 2.0002 e to the minus t. right? That's the full analytical solution. So what you have here is that y, so if when t is equal to 0, y is equal to 1. So graphically, this is going to start at 1, right? But then the slope, so quickly this one goes away, right? And so then this then has a longer, sort of longer decay, right? Sorry, this starts at, yep. And then this will go away quickly, so it sort of quickly shoots up and then decays. All right, so this is stiff because you have, look at this, 1000t and then negative 1000t and then negative t. So you have two very different time scales. And so if you're actually integrating this, you would have to be really, take tiny steps to actually resolve this initial jump, and then you have this really slow decay going on, where you could take much larger time steps. So this is stiff. So this is a lot of error will accumulate based on the choice of time. So there are actually special algorithms that are used to either detect stiffness, or when you have stiffness, to use those algorithms. So again, this is just kind of scratching the surface. It's not always plug and play. For the most part, we have some pretty robust algorithms. If you're using MATLAB, or if you're using kind of Python, basically Python, SciPy packages that'll sort of help you along the way. But again, user beware. This is kind of the consequence of digitization and discretization. And if this is the physics equation, something like this, if this is the equation of the physics you're trying to solve, it can get hairy. Okay, so I'm going to finish with just a picture, probably a famous picture. This is called the Lorentz tractor, and it's actually just three simultaneous differential equations, ordinary differential equations. And you can think of it as x, y, z, and that's why this is plotted. And usually you can see this rotated, and people do different things. But the point here, this is a very simple dynamic problem, where ultimately, if you have a slightly different starting point, your y initial, like x, y, z initial, and it could be 10 to the minus 12 different. What's going to happen is the divergence between those two paths, if you were using a measuring rod between those two paths, and if it starts at 10 to the minus 12, it's actually going to exponentially separate. So the point where two different solutions can be on two of these different attractors. So this is the root of chaos theory. And so there's some beautiful videos. If you want to get into it, go take in. There's so much richness. I can't even get into in a little 20-minute thing and wipe the board. So maybe I'll come back to doing a little bit of chaos theory, but even these basic tool sets are enough to even explore some of the basic stuff. And so there's really interesting dynamics. And chaos theory is, Lorentz tractor was actually modeled as he was trying to model some basic weather patterns, and he saw chaos. And so if you're ever getting mad at the meteorologists for their prediction, the answer is some of it is just a dynamical system for which there's chaos. If you don't perfectly have all your starting conditions right, you quickly diverge. So anyways, so much more there it's not related to numerical discretization, right? It's not numerical error when you have these issues, right? When the weather person isn't predicting well, it's not a numerical error issue. It's actually chaos. It's actually built into the equations, the sort of growth and the uncertainty. So anyways, fascinating stuff. We'll see you next time.